Let us take this example considering a two area interconnected problem. Area 1 is characterized with a load of 20,000 megawatt and generation ability of 19,000 megawatt. This is suffering 1000 megawatt deficit, that is noted here. And another area having 40,000 load and 41,000 megawatt generation. It's having, from the numerical approach, 1000 megawatt excess generation than the load. That 1000 megawatt is flowing from area 2 to area 1 to make this interconnection successful. That's what is the scenario graphically represented here. Then you have been said the group characteristics and frequency response of the area, nothing but the dependency of loads on frequency is mentioned by D as 1. 1 refers to common, R is 5%. Then we have to take this D and R respective to area 1, respective to area 2 on their capacity and conversion. Then the connected load is at 60 Hertz, because I said this problem is taken from US periphery, 60 Hertz, and is 20,000 megawatt in area 1 and 40,000 megawatt in area 2. The load in each area varies 1% for every 1% change in the frequency. That's what is the nature of the explanation for D. Area 1 is importing 1000 megawatt from area 2. That is what is graphically shown. There is a deficit of 1000 megawatt in the area 1, and area 2 is having an excess generation. It is default importing to balance the particular area's megawatt activity. The speed regulations are respectively are 5% for all units. Now, area 1 is operating with the spinning reserve of 1000 megawatt and spread uniformly over the generation of 4000 megawatt. So what is the meaning of this statement? There is a generation of 19,000 megawatt in the area 1, and this total area is having a capacity of 1000 spinning ability. This spinning reserve is accommodated only on a certain generator which are of capacity 4000. It is not that 1000 is shared by all the generator quantifying 19,000. There are only few generator totally adding this 19,000 megawatt, out of which 4000 megawatt addition what they are getting done, only those generators are carrying the spinning reserve ability. That is the meaning of the spinning reserve of 1000 megawatt in this area 1 is spread, allocated uniformly to the 400 megawatt generating capacities only. And area 2 is operating with a spinning reserve of 1000 megawatt. Again, this is also having a spinning reserve of 1000 megawatt spread uniformly over 10,000 megawatt. Its generation is actually 41,000, but spinning reserve of 1000 is additionally a burden or ability of 10,000 megawatt contributing generators, maybe one generator, maybe 10 generator, like that. Whatever is that pool, some group of generator, total capacity of them is 10,000. They are titled to share 1000 contingent energy as a spinning if it is required. Similarly, at area 1 it is 4000 megawatt out of the 19,000 total capacity. Then determine the steady state frequency, generation and load for each area and a tie line power for the following cases. See, the problem itself is a page of length in the presentation slide here. In case of it is an printed textbook, almost 3/4 of the page is covered by a problem itself. Therefore, we should have a lot of peace of mind to understand the problem of a problem. If we are able to get the problem, what this is focusing to us, probably solving will be easy, otherwise it remains as a problem unsolved. Therefore, a peace of mind and small technical thinking about the parameters given, if you use, probably you are able to touch the problem. Okay, let's say determine the steady state frequency, the new state of operational frequency and deviation if I find it out, generation, the contribution from area 1, area 2 to balance the megawatt exchange, and load for each area, and tie line power flow, what is to be exchanged for the following cases. The one is, if this system is having a parallel operation, suddenly experience a loss of 1000 megawatt load in area 1. 1000 megawatt is lost. Then assuming that there is no supplementary control, this we must be very careful. You are trying to make these two systems which are sharing, which are interconnected without the supplementary control, means only primary loop is functioning. Suddenly area 1 experience drop of 1000 megawatt load. Then what will happen? Then how these areas are going to balance that 1000 megawatt loss? That is the situation. So definitely when there is no supplementary control, both the areas are going to respond for the change. When there is a drop in load, frequency shoots up. That's what we can assume, and we can start thinking in that direction. The second is each of the following contingencies, situations. For each of the following situation, when a generation carrying spinning reserve in each area on supplementary control. See here, supplementary control is put on each area, area 1, area 2, with frequency bias factor like beta, whatever the beta, nothing but 1 by R1 plus D1, 1 by R2 plus D1, whatever we say. Frequency bias factor 250 megawatt per 0.1 hertz, and in area 2 500 megawatt per 0.1 hertz for area 2. This is a situation if supplementary loop is having such a characteristics. How is that loss of 1000 megawatt is worked out by the situation? So if we understand these two very clearly, we are able to understand the problem of this particular representation, and we will see loss of 1000 area 1, loss of 500 megawatt in carrying the part of the spinning in area 1, 2000 megawatt. So it is similar problem which yesterday we just took. Similarly, it has been originally taken from Dr. K. Prabha Kundu text. I'll be referring over it. With no supplementary control, let us visit the problem. This situation, parallel operation of these interconnected areas for the capacities mentioned with the droop and frequency sensitive load nature given for a loss of 1000 megawatt in area 1, assuming there is no supplementary control. How to function? Then let us go with no supplementary control as a title, assuming that none of the governors are blocked. All the generating units in two areas respond to the loss of load, because it's very simply understood. When there is no particular supplementary loop action, so 5% droop which is there on area 1, area 2 need to be converted as 1 by R1, 1 by R2 and equivalent droop, because that has to be used to compute the frequency deviation. Then to go ahead with that, a 5% regulation on 20,000 megawatt capacity, including spinning reserve, that is 1000, you can see 19,000 megawatt and 1000 spinning, which is not accounted here, which is to be taken as a net possible load possible in this area as 20,000. Then 1 by R1 is computed. Instead of calculating R1, 1 by R1 is computed, because in the equation 1 by R1 plus 1 by R2 refers R equivalent. Then to place that way, it is done. 1 by R1 equal to 1 divided by 5%, 0.05 into the capacity of that, because I want that representation of droop by megawatt per hertz, because it is easy. The composite response of this particular area 1, area 2 is also given in the form of megawatt per hertz, 0.1. If I shift backward, it will go megawatt per hertz, megawatt per hertz. Then we have to make this R1 also 1 by R1. If I take, this will become megawatt per hertz. Then it is 1 by 0.05, a fraction, into capacity of that area and frequency what it is working. So therefore, when I take this operator, it is going to become 6666.67 megawatt per hertz as 1 by R1 for a 5% at the capacity of that particular area and frequency with which the system is operating. Similarly, in area 2, 1 by R2, again it is a 5%, but it is on what basis? 42,000. 41,000 is the total generation, 1,000 is a spinning reserve there. It becomes 42,000 with the frequency 60. When I take this ratio, it gives me 14,000 megawatt per hertz. So therefore, I could get R1, 1 by R1, 1 by R2 in megawatt per hertz. The total regulation due to interconnected total capacity, 20,000 over there, 42,000 over here, 62,000 megawatt capacity is with the two areas is 1 by R equivalent. 1 by R equal to 1 by R1 plus 1 by. Why it is being done? To calculate the frequency deviation. Look at the footer of this page. Frequency deviation is step change in load divided by 1 by R1 plus 1 by R2 plus D1 plus D2. This is nothing but I have to write this in the expanded form. Instead of writing it in expanded form, 1 by R capital refers to 1 by R1 plus 1 by R2. What capital D refers over here? D1 plus D2. That is the reason it is being worked out separately. In few of the problem it is being done. In much of our earlier discussion, we have not done very explicit as 1 by R1 by R2. Directly we took R1, we took R2, positioned as a 1 by R1, 1 by R2. So you can still work in that way also. Therefore, 1 by R equal to 1 by R1 plus 1 by R2 stand as 20,666.67 megawatt per hertz. Similarly, load damping constant, the reflection of loads for the change in frequency. So load damping in the first area, that is here, for the 19,000 capacity what I have here, you can just see here. Okay, so 1%, 1% 1 divided by 100, 19,000 megawatt load remaining after the loss of 1,000 loads, because we are studying a case study of what? Loss of 1,000 megawatt in the area 1. It is nothing but 20,000 minus 1,000. It is 19,000 prevailing. 19,000 divided by 60. So this 100 100, it's very typical. 1% and 19,000 divided by 60 into 100, representing it into megawatt per hertz. So I suggest this 100 can be taken out. One of the earlier calculation we have seen not being mentioned. Directly D value, capacity divided frequency was mentioned. You would have taken that advantage. So when I mention converting this D 1%, 1% change in load for every 1% change in frequency, we converted it into megawatt per hertz like this. So the area's reflection from area 1 refers for every 1 hertz change in load's frequency, power variation is 316.67 megawatt. The impact of this meaning is 1 hertz change means 316.67 megawatt alter. That is a reflection of D1. Then similarly, load damping due to 40,000 load in area 2. So that stand as 1%, again 40,000 divided by 60. So it is 666.67 megawatt per hertz. So we could get 1 by R1, 1 by R2. We could get D1, D2. Now we are in a right position to write D equivalent. I can add them, or directly I can write due to the change in load of 1,000 in the area 1. What is that deviation in the frequency? One would note delta F or delta omega equal to. So it is delta F because I should speak delta F because I am getting this D1 and R1 in terms of megawatt per hertz, not in per unit. When it is in per unit, I can speak delta omega or delta F because they are having PU value. I can use delta F or delta omega. Now I should speak delta F only because of hertz at the one of the unit here. So delta PL divided by 1 by R1 plus 1 by R2 plus D1 plus D2. Because this is an interconnected area, the reflection from both the area should be taken into consideration. Once I write it, so loss of 1,000, and you should be very careful. The bracket, inside the bracket, it is a minus 1,000. So otherwise it is directly a shift in load means minus delta PL refers change in load. Usually incremental loads are put numerically. 1,000 increment means minus 1,000. Inside the bracket, delta PL1 is put as a minus means what? This delta PL is decrement of load. Hence minus is attributed to that. This change you have to know because this quantifies your answer. When there is a drop in load, definitely frequency increase. That consciousness if I have, taking minus over here plus over here just to make my path to go. So because it is a drop of 1,000 load means frequency shoots up means this must be an additive to the base frequency like that. So when I substitute 1,000 minus and minus outside and beta 1 beta 2, nothing but 1 by R1 plus D1, 1 by R2 plus D2 refers to beta 1 beta 2. These are nothing but beta 1 beta 2's equivalent representation. Once I take them, I'll be getting 0.04619 as a deviation in the frequency. So this deviation quantifies the new frequency. So what will be the new frequency at that time? 60 hertz is the base frequency in this problem. 60 hertz is the base frequency. So 60 hertz plus 0.04169 is the new frequency standing. It is not written directly here. It will be written later, but we can definitely say what is the total, the new frequency of operation due to the loss of 1000 megawatt in area 1 is quantified as 60.04169 hertz at the footer you can see here. Now, as we experience, the area is having D1 and D2 like that. Definitely due to the drop in load, frequency shoots up. Because of that, D1 and D2 characterized for both the areas. There will be a change in load response. If the frequency changes, load will change. What is that change in load happened due to the change in frequency? That is called deviation. That I have to quantify. This is an imaginary load getting changed in the area due to the actual megawatt change what is happening. Therefore, delta PD1, the change in load in area 1 is D1 into delta F. The frequency can say damping ratio of the area 1 into deviation, which is 316.67. This we have worked out here. D1 is there is a change of 316.67 megawatt for every 1 hertz change in frequency. In that way, D1 into delta F, if I work it out, it results me megawatt, because it's megawatt per hertz. This is a hertz. Hertz cancels, and this remains as a megawatt. Therefore, earlier what we were doing, we were writing them in PU, and we were converting it into base, multiplying by base value to get the megawatt like that. So 14.63 megawatt is the change in load experienced. Let us say, let me write second and let us discuss. PD2, delta PD2 is the change in load experienced due to the frequency deviation occurred in the interconnected operation is given as D2 into delta F, which stand as 666.67 into 0.04619, which stand 30.79 megawatt. Now, what these 2 megawatts explain us? Due to the drop of load, frequency got shooted up. Due to the increased in frequency, these loads are increased. Unknowingly, these two are the growth of load in the area. There is no doubt 1000 megawatt is eliminated from the area 1, on the elimination of which frequency got shooted up. Because of that rise in frequency, these two are the invisible load added to the system respectively in area 1, area 2. So we will be taking care of this because we have to manage the system in a balanced state. So these two need to be taken care. Then, due to the frequency deviation, whatever we have seen here, the frequency deviation of 0.04619 hertz. Because of this is occurred because of the change in load of 1000 megawatt in area 1. What is that? Proportionate pickup of this disturbance. We call this as a disturbance. Disturbance may be either drop of load or rise of load. So this disturbance created the deviation here. This disturbance is shared by both the areas in proportion to their capacity and characteristics. What is that share of area 1? Share of area 2 we would like to quantify. So share of area 1 is delta F divided by R1. Delta F divided by R1. But we know 1 by R1 already. In the previous part, what was 1 by R1? 1 by R1 is 6666.67. This is worked out. 1 by R1 is worked out. So simply it is being used here. So delta F into 1 by R1. 1 by R1 is 6666.67 into this particular value. So therefore, this resulted me 307.93 megawatt. We'll see what is this shortly. This is numerically 307.93. Similarly, what is that proportionate pickup in area 2 for the drop of 1000 megawatt is delta F by R2. 1 by R2 is also, we got similar to the 6666.67. We got it as 14,000 into deviation. which led me 646.65. So what are these things? Are these the command to increase the generation or decrease the generation? I should be very careful about this. Generally, if you remember the statement of the problem, there is a drop of 1000 megawatt load in the area 1. What the drop means? Generation is surplus. You have to reduce the generation. This is the indication that 307.93 megawatt decrement in the area 1 should happen. Similarly, 646.65 megawatt decrement in the set point of the generating area 2 should happen, so that drop of 1000 is worked out immediately by the both the areas. This is because the absence of supplementary loop, both the areas are responding for the change in load either in area 1 or in area 2 or simultaneous to both the area. So therefore, this is how the problems are so beautifully arranged to see to that effect of absence of supplementary loop, effect of presence of supplementary loop in a single problem. So therefore, once supplementary loop is not there, this is a decrease in command at area 1, decrease in command at area 2. Respectively, when I summarize this situation, the total area 1, area 2 summary, 20,000 was the connected load here. Can you see here? 20,000 was a connected load, 1,000 was flowing from this area. Okay. And suddenly there was a drop of 1000 megawatt in area 1. So 20,000 load minus 1000, 19,000 is the prevailing load. And due to the rise in frequency, 14.63 megawatt is growth of a load. That is say plus delta mean plus 14.63. Together, total load after having 1000 megawatt rejected or reduced is 19,014.63 megawatt. Then you can look into the generation aspect. Generation was 19,000 megawatt. Origin this problem was focusing you. It is a generation here, 19,000 megawatt, and you are borrowing 1000 megawatt and you are making cope up of 20,000 megawatt, having 1000 spare energy if required. That was the 1000 megawatt spare spinning energy floating. Right now 19,000 and 1000 was making a balance of 20. So this is how this particular value says generation was 19,000. Now due to 1000 drop in the area 1 load, there is a command to reduce the generation by 307.93. You can see 19,000 was a generation, reduce it by 307.93. Your new generation should stand as 18,692.07 megawatt. So this is how numerically a megawatt you have seen. Economic scheduling the aspect of generation, if you consider a 1 megawatt matter, you are great because it's in terms of lakhs together amount over a month and over an annum, it will count for you. Hence, it's very sensible, even though numbers are very negligible and very small by value, but their impact on a total quantum is very large. So this is how area 1 is put to steady state after 1000 loss of megawatt loss of load in the area 1. These are the revised computations or values existing. Similarly, in area 2, what would be the situation? It was having a load of 40,000 and suddenly this 30.79 megawatt is growth noticed added to which 40,000 30.79 megawatt is the new load situated on that plant. And the generation, when we say 41,000 was the generation in that area, just you can go back and see, correct? 41,000 megawatt generation, and it too had 1,000 megawatt load, I mean a spinning reserve spread on 10,000 megawatt. Totally I have generation right now encashable right now is 41,000 megawatt. So this 41,000 megawatt is commanded to reduce the generation by value 646.65 because 1000 megawatt is decreased. Hence it is to decrease its generation by 646.65. Now you may ask me a question, why it has to respond? Look to the diagram. This area 2 is sharing a load of how much? 1000 megawatt on the tie line here. So once there is a drop of load here, this power is flowing. If this do not respond, this will be unbilled for this. It is not being taken care. So therefore, this area has to reduce the generation as per the commitment. So therefore, you will find 41,000 minus 646.65 as the reduced command as 40,353.35 megawatt as its new generation. So now you will see from the total transaction viewpoint, tie line power flow from area 2 to area 1 is 322.56. Why? How you got this? This you got as 646.65, and this value, if you account, it was 1000 earlier. 1000 minus the reduced load. What is that new load? Only this much is flowing. It means there is a decrease of 646 megawatt in the generation. Then how much it is being delivering to the area 1? Area 1, it is only 322.5 because this is 1000 minus this. 1000 was flowing from area 2 to area 1. When you reduce this, normally you'll get 322.56 as a megawatt. So this is how decrease in tie line power has come. This was asked. What is that question? Change in frequency, new value, which is shooted up. Change in tie line power, share of load, individual set points, and new values of generation. This was the question asked to us here. You can see. Determine the steady state frequency, generation, and load in each area. Tie line power flow for case number 1, case number 2. So one bit we answered, having understood this problem this way. About 3 slides of calculations. Similarly, with the supplementary control, just you can visualize with the supplementary control when I use the word. What is the case study? 1000 megawatt loss in the area 1. When the supplementary control comes, the area control error is of 1, area control error is 2 come into picture. They are delta P12, beta 1, delta F, minus delta P12 or plus delta P21, beta 2, delta F. So these two make the balance. Ace of 1, ace of 2 has to be always 0, so that whichever the area is suffering a loss or growth of load, that particular area's ace will simulate the set point change in that area, and in that area, if there exists a capacity, that ace will respond for the change in load. The other area which is not experiencing any change in load would make its ace value 0. The integral controller is not going to change. This is very simple. When a loss of 1000 megawatt in load area 1 is mentioned, you have to just say area 1 generation and load are reduced by 1000 megawatt. There is no steady state change in area 2 generation and load for the tie line. What was going just will flow, generation and load and tie line flow. So there is no change. It was already accepted. The change in load is in area 1. Area 1 generation has to reduce. That's all. You can see here. Area 1 generation and load are reduced by 1000 megawatt. There is no steady state change in area 2. Area 2 is not going to respond. And load in that area. And tie line power flow. It is pumping 1000 constant power. See here. It is borrowing 1000 continuously. And it is balancing its requirement. So this is how supplementary control will make the control of that area's generation according to the changes in load in that area. That change in load will not affect the committed areas which are exchanging the power. That is the advantage and knowledge we get from supplementary control. And very sure, the ace of that area, delta P12 and delta F, when I substitute over here, this turns out to be the actual step change of 1000. In the earlier derivation, we have seen change in load in area 1, ace become equal to the change in value. Change in area 2, ace 2 automatically become change in load 2. And ace in both area become equal to their respective changes. If the load change occur in both the area, this could be another case. Then ace 1 refers to change in load of area 1. Ace 2 refers to change in load of area 2. Together make the balance of 0 error. Then both the areas will strive to meet their requirement with the existing capacities and make the things possible. This is how this kind of problem you may expect. So I hope this part 1 with the supplementary, without supplementary, we can focus more. That will quantify our requirement. Okay. This spinning part of the area is little additional thinking. Mostly I don't find these are of our capacity or of our requirement this time. So, but it is there. It is there in the printout because that textbook is one of the textbook for masters and other research activities as well. From that text, problems were picked for the study as a compared to knowledge. Okay. So I just make this problem over here, and these additional things which are there in this presentation are already there for your review. You can just go through and you can get it. Okay. Just momentarily I will make the things visible to you in the video. You can just look forward that. When the loss of 2000 megawatt with the spinning reserve, not having any spinning reserve, how it is being worked out. Computation techniques goes very similar, but the statement when we quantify with the case, they stand as my reflection. That we have to look forward. Okay. Tripping of tie lines. When tie lines were broken, not delivering, definitely 1000 megawatt which was going to the area 1 get blocked here. So how that system is going to cope up is the another tripping of tie lines concept is presented here. And how is that area? Now you can see once there is a tripping of tie lines, you can see frequency at area 1 is different, frequency at area 2 is different. Can you see? So this is experience when there is a bifurcation. When there is a trip of transmission line between area 1 and area 2, each area become isolated area now. When they are isolated area, their frequency deviation, working frequency, its working frequency will be definitely different because they need not be swinging in hand. That time it's a change in frequency drop due to load, and there is a rise due to reduced load, which was delivering to this trip of load through the tie line has happened, or tie line is opened. So there is shooting up of frequency due to the loss of load for this which is experienced. This way, this problem give you overall insight of interconnected mode of operation only. So for us, type 1, type 2, which is of sharing without supplementary control, with the supplementary control, change in frequency deviation, and change in generations, and change in tie line power. That kind of 3 parameter computation we need to be careful. So I try to suggest you at least go through those 3 parameters of your computation. Then moving to the last bit of this problem, particular chapter, state space model of ALFC in interconnected operation. For that, this one diagram, just you see how that implementation of automatic generation controller in a centrally managed system or in energy control center takes place. This is how one continuous sequence diagram. So how do you allocate power to the individual plants? You allocate the units to the respective plant to generate certain P reference to every 5 seconds. There will be a command. If you just will look into the SCADA and supervisory controller data acquisition system in energy control center, then the master slave computer, then the role of computer, role of dispatcher, what are all the key functions that SCADA is going to function. In that way, the allocation of units to respective generator takes place with respect to time slice. Every 5 second time slice, there will be a revised setting of power generation to each generator keep on taking place. Then for that, the other issues are economic dispatch, governor response, energy balance, all were the input to this computation block. This computation algorithm take all these care. One is economic dispatch, governor response, energy balance of that particular unit which are going to operate or which generator are going to command. Along with that, what is that error you are getting? The area control error, whatever the area control error is the stimulus for additional generation requirement, that whether you have to increase or decrease. So that, yes, and these values together transform this as a power set point. So this will be one implementation logic. For this years to come, we have here. So we have set frequency, and we have measure of tie line power flow, then mixing this entire measure frequency, actual frequency, measured power, tie line power into a ACE, and ACE is probably conditioned. This is filtered. It means we have to condition the error above, below, process it, and then you make an amplification with the gain and integrate this. This is called integral controller. This is a pictorial representation of the controller what we have seen. It means measure of tail and power flows, measure of actual frequency, and set frequency, deviation, and operating it as a ACE, and magnify the particular errors, integrate the error, get it as a signal for the allocation controller algorithm or controller program with all these other associated parameters to see to it that every 5 seconds update will go to the clients. This way, this will be implemented in the energy control center. One outline. Then for this, it requires representation of the system. Then we have something called as state space model in an isolated system, which we have seen. This diagram show you the frequency representation, or we can say yes, domain representation of the isolated system having a governor in with a first order lag function, a turbine, a mechanical aspect with the first order lag function, and generator and load in a interconnected area. Means in a area, not in between the area. It is isolated area, area's load, area generator only. One a single area, we can say. Generator plus load, and its droop with a deviation fed back as a primary loop to control the mechanical supplement. Then with the frequency deviation with the integral controller to cause a reference point changing. Reference point changing for the governor to situate as a supplementary control. This is just a complete ALFC in a single area, and load in that area, whichever is going to change. Then you can see for each for the governor, the stimulus is P reference point. Any change in P reference point will cause the valve displacement by the governor. And for the turbine, any valve open close will definitely modulate the input fuel to the turbine. It will change the mechanical input to the mechanics. Then this mechanical change requirement is due to the change in load only. Then the balance has to happen here on the energy system representation. What is that deviation is going to reflect? If that is worked out by primary loop, fine. If it is not being managed by the primary loop, then the same feedback with the integral controller is connected to set point changer. Whatever the P reference point and the actual computed power from the feedback, which is becoming an input to the governor. If it is not able to cope up, the reference point shifting is also done by integral controller. Integral controller keep on modifying the P reference point as and when delta omega is not 0. So this is going to respond continuously and keeping this updated P reference and the computed power from the feedback compared, and this error is fed to the governor. Governor will change the valve position and subsequently mechanical change the mechanical power as well to balance the electrical loads. Energy balance can be written here. This is what are the scenario. Ultimately, in this state space model represent, what we'll be doing, we are trying to connect each block of representation over here by transfer function and generate one S domain, frequency domain equations for each block. Then write them as a variable, state space variable as a variable list in the form of a vector. Then represent them by a matrix, row by column. Then that become a representation of the state space model of the isolated system in the form standard. So AX plus BU plus and CX plus DU format. So for input vector and output vector, how we write it? So we have to write one generalized equation for this model. To do that, what is basically required? Understand each block. What is the transfer function of each block? We must know input and output of that represented by a transfer function of the activity, what the governor, turbine, generator load area are represented. Let's go ahead. So again, I took the same diagram over here. Then look at the S domain equations at this point, at energy balance here. Can you see this? So delta PM S minus delta PLS. Can you see this bracket? Delta PMS minus delta PLS on whose operation 1 by 2 HS plus the load get you frequency deviation. I'm trying to write the situation at this summing block and right hand side. So balance equation, delta PM of S minus delta PL of S into this block function 1 by 2 HS plus D refers to delta omega of S. From this, I have to simplify this equation into a simpler one such that this 2hs plus d I transfer other side and simplify. How I do it? Delta Pm of S minus delta PL of S is equal to what? You can see here. Delta Pm of S minus delta PL of S equal to delta omega S into the quantity transferred to the RHS, which is written as 2HS plus D. Once I simplify further, because I want to write them in the form of variable transition matrix. So therefore, it become S into delta omega of S equal to what? So S into delta omega S into 2. Let me split first. I will take this delta omega S into this bracket. It become definitely delta omega S into 2HS plus delta omega S into D. Then I will make the heading of the equation as delta omega S. Then what I can do? S into delta omega S equal to this function, if I transfer other side, become minus D minus this divided by D 2 by 2H, which is our delta omega S multiplied with this term is there. It has been transferred other side. So minus D by 2H delta omega S plus these terms 1 by 2H delta Pm of S minus 1 by 2H delta PL of S. So this become S into delta omega S in equation for me. Then for the turbine, when I come to this turbine block, how this functions? For this turbine block, input is delta PV of S. The change in wall position is the stimulus for this turbine, the output of which is delta Pm of S. If I get a transfer function, means what? Delta Pm of S over delta PV of S is the transfer function 1 by STTR, like this way, which is written here. Input into transfer function refers to output available from that block. This is for the turbine representation. Input into turbine block transfer function refers to output over here. Similarly, I quantified all these things over here. Can you see here? Turbine input is delta PV of S, whose output is delta Pm of S. Then if I represent this, you can see 1 plus STTR into delta Pm of S refers to delta PV of S. Correct? Once I take this simplification, 1 plus STTR into Pm of S refers to delta PV. Then what is this S into delta Pm of S? Rest all I transfer the side. So I'm taking the heading as S delta Pm of S. I split this bracket. Then I transfer everything on the right side except Pm of S at the left side. It become minus 1 by TTR delta Pm of S. One of the term with respect to 1 comes other side plus 1 by TTR into delta PV of S. This is another representation we get from turbine block. Then for the governor is again a first order lag function whose input, whose output. If I quantify, you can see output of the governor is what? Input to the turbine block. Delta PV of S is the output of the governor. Then for this input is the reference point minus power computed from the shaft. This is delta omega S by R means what? Feedback path. I just go back here. Delta omega of S divided by R is coming over here, and delta P reference minus delta omega by R is called power set point, power computed from the shaft rotations. That difference is a stimulus for the governor. That's called input over here. The term what would have been here is delta P reference of S minus delta omega S divided by R. That's what I have written here. That is the input. Then output of that governor block after the first order lag representation, transform this as the change in wall position. If this is the case, how do I write this? You can see here delta P reference of S minus 1 by R delta omega of S into this transfer function refers output delta PPV. Then I try to simplify this, making this bracket open, transfer other side. You can see delta PV of S into 1 plus STG. I took RHS side equal to delta P reference S minus delta omega S by R. Then again, what is this S delta PVS? I hold here. I hold the variable delta PVS with S LHS side. Rest all I move to the RHS side. That refers again minus 1 by TG delta PVS plus 1 by TG delta P reference of S minus 1 by TG into R, 1 by RTG delta omega S as another equation concerned to governor. When I look for the integrator, just I go back here for this integrator, the input and output of this. If I connect delta omega of S and delta P reference of S, how I can write it? You can see here. Delta P reference is equal to integral controller into that taken out here. Delta omega S operated on integral controller transfer function K1 by S, and I'll be getting reference point setting. Then with which S into P reference of S equal to minus Ki gain of the intercontrol into delta omega S. So I got all these functions represented by simple equations. So these equations are written in this way. We can define the state vector in time domain as in the form of omega t function with a time based. The state vector x is delta omega frequency deviation, the change in mechanical powers, change in wall position, change in reference point settings, and in a column vector I want, hence I wrote transpose this vector in the transpose manner. How many I have? 1, 2, 3, 4. These are the 4 variables in the particular vector. So they are called state variables. The state variables are frequency deviation, change in mechanical power, change in wall position, change in reference settings of each area, and the transpose is a vector to write in the column manner. Then an external input. What is the external input for the total mechanism here? The external input for this is load change. This is the load change. These are all the input outputs inside the system. The external input is load change. That is written here. The external input is delta PLS. Now the state equation can be transformed into time domain and written in the form of matrix as delta omega dot, we write as a cap, delta PM dot delta PV dot delta PREF in the form of a column vector equal to what I'm writing here now. This delta omega is an equation. This is a matrix, a row and a column and a constant. So delta omega is taken from what? Delta mean minus d by 2h into delta omega plus 1 by 2h into delta PM plus minus 1 by 2h into delta PL. Means this is one of the equation we got. Where do we got this? Let's go back and see. Here is the equation. S into delta omega S is the equation. This equation I represented in the form of a matrix. So delta omega S in a transition minus d by 2h delta omega S. The first value is minus d by 2h delta omega. Second is 1 by 2h delta PMS. The third is minus 1 by 2h PL. Who observe these constants? Minus d by 2h, 1 by 2h, minus 1 by 2h with omega, with PM, with PL. You can see here. Minus d by 2h with omega, 1 by 2h with delta PM, and you have minus 1 by 2h with delta PL. What I did here is this equation, the frequency deviation, what is being noticed by the isolated S domain representation of the ALFC, this equation is written in the form of coefficient in matrix. So the first equation is represented in this manner. So therefore, what is delta PM? Delta PM is the energy balance at respect to mechanical output. This is again represented from turbine. You can see here. What is delta PM? Delta PM of S is minus 1 by T TR PM, 1 by T TR PV. PM PV operating on 1 by TR minus 1 by TR plus. You can just see TPM. You can see minus 1 by TR with the second state variable. First variable is omega. Second is PM. Minus 1 by TTR PM. 1 by TTR PV. So this is second equation. There is no constant addition from the third. 0 0 into PL. Similarly, we wrote the PV and P reference like this. Okay. Delta omega transition matrix, the state variable, delta omega cap, delta PM cap or a dot, delta PV cap, delta P reference cap. From the equations respectively, I can fill them, and the state variable I can mention plus the constant what is going to add. This become the matrix form of representation of the state equations, and it is in the standard form. What is that? xt equal to xt cap, what we call it as axt plus bu, ax plus bu format, and cx plus bu inputs, input state vector and output state vector x of t y of t in the form ax plus bu cx plus du. So where x of t is a state vector, which is nothing but I have defined here, state variables are here. Then u of t is the input vector where we have inputs mentioned from that. Then y of t is the output vector. Then we know x of t is actually the state vector delta omega, delta pm, delta pv, delta p reference, transpose of that, because it's in a column matrix. U of t is the input vector. What is the input vector for me? Load is the input for me. Output is the omega, the change in frequency deviation, delta omega. So this is the representation. We do not have much things on this, but it is state representation. We should know how it is represented in a state matrix. Then further it is separated as A and B, C and D matrices. From this A, B, C, like this is written as a split matrix. You can see minus 2H, 0, 1 by RTZ, Ki. This matrix is written as matrix A. Then minus 1 by 2H, 0, 0, 0. 0, 0, 0. Can you see this? Minus 1 by 2H, 0, 0, 0. This is matrix. And matrix C and D. D is 0 here. C is 1, 0, 0. So C is 1, 0, 0, 0 to balance the equation. So this is written in AX plus BU, CX plus DU format using A, B, C, D. A and B I can find here. A and B here directly. And C and D are represented to balance my equations of this particular AX plus BU, CX plus BU.